Hello Physics 1 students and welcome to your Lab 9 Prelab video. Today we're going to be talking about inclined planes. And to start us off, I'm going to share with you my absolute favorite physics meme. So we have snakes on an inclined plane, which is what we're going to be talking about today. Snakes on a Cartesian plane, snakes on a three-dimensional plane, and snakes on a plane. All right, so some things to know before we get started. Should all be review. Newton's third law, for every action there is an equal and opposite reaction. And we want to be thinking about this in terms of normal force today. And normal force, for review, is the upward force that is perpendicular to a surface on which an object rests, and it is equal and opposite the y component of the object's weight force, which weight force is mg. This is equal to the weight that the inclined surface feels. So you can see there's an inclined surface over here, and it's going to be equal and opposite to the weight that this surface is feeling, which, as we're going to talk about in a little bit, is mg cosine of theta. And then one other thing just to keep in the back of your mind, even though we're not really going to be dealing too much with problems that have friction today, you probably will have this in homework problems. Remember that force of kinetic friction, Fk, is equal to your coefficient of kinetic friction, or mu k, times your normal force. Okay, so just keep that in the back of your mind. As I mentioned, we're not going to really be doing too much with friction today, but it might come up in your homework. Okay, so normal force on a horizontal surface. So yes, I know I said we're talking about inclined plane motion, but let's just start off with simple examples and see how forces can impact normal force on a horizontal surface. So right here in this example, we have an upward y component to our force. So you can see we've got this mass. It's resting on a horizontal surface. We have this pulling force at some angle theta, and you can see that there is the horizontal component, which is Fx pull, but there's also a vertical component to this force, right? And that's kind of what we want to focus on here, is Fy pull. Okay, we have an upward component to our pulling force, and that is going to impact our normal force, right? Because if you think about it, the normal force is the force that is equal and opposite to the weight force that a surface is feeling. Well, this Fy pull is diminishing that weight force that the surface is feeling. So that means our normal force is going to be less. Okay? I am going to go through the x-plane, even though we are kind of focusing more on normal force right now, just because maybe it'll help you with your homework. Because a lot of times you'll have to calculate what the acceleration is, and of course you're going to be using the x-plane for that. So if we sum up our forces in the x direction with this drawing, you can see that we do have a frictional force. So we're going to have Fx pull, that's what's driving the system, producing this acceleration, right? But it is being counteracted slightly by this frictional force. So we have Fx pull minus our friction force is equal to the total mass of the system. Because remember, this could be an entire system of masses connected by a string or some other means, not just a singular one. So total the mass of the system times the acceleration. All right, so if you were looking to find acceleration, this is how you would calculate it in this example. But what we really want to focus on here is our y direction, right? And how this Fy pull is influencing our normal force, right? And as I mentioned, it should be diminishing that normal force, right? Okay, so when we add up our forces, we have normal force is positive because I've defined up as positive. We have Fy pull also positive because it is also upward. And then our weight force is negative because it is downward, right? And this is going to sum to 0, right? As we've talked about numerous times, we have no acceleration in the vertical, right? There is only horizontal acceleration. This mass isn't bouncing around up and down. Okay, so that we know that this is equal to the total mass of the system times an acceleration of 0 in the vertical, right? So we can rearrange this equation in order to solve for our normal force. And we get that our normal force is equal to our weight minus Fy pull, which is exactly what we would expect, right? We expected that our normal force was going to be less than our weight force because Fy pull is diminishing the weight force that the surface is feeling, right? Now we're going to do the same thing, horizontal surface, but this time we're going to have a downward y component. So now we have this pushing force and we're pushing down on the mass. So you can see Fy push has a downward component, right? Not upward, it is a downward y component. Okay, so I'm not even going to go through the x direction because it's exactly the same as it was before. The y direction is what we want to focus on here. So how is this influencing our normal force? Well, once again, up I'm defining as the positive direction, so the normal force is going to be positive, but this time, because Fy pushes downward, that's going to be negative, so we subtract that. The weight force, still negative, so mg minus mg. No acceleration in the vertical, all horizontal component, right? So we know that this sums to 0, all right? Well, we know that the acceleration in the vertical is 0, right? So we can rearrange this equation and we can solve for the normal force, right? And we get that the normal force in this case is mg plus Fy push, right? And this makes logical sense. The surface should feel a force that's greater than the weight force because Fy push is adding to the weight that the surface is feeling, right? We're pushing down on it. So this surface is feeling more than mg. It's feeling mg plus Fy push, right? And that's exactly what we see. So if we move on now to normal force on an incline, you can see now we have a mass and it's sitting on an incline at some angle theta, right? And so because this is resting on a surface, there is going to be a normal force, right, which is going to be equal and opposite to mg cosine of theta, not the whole weight force this time. The reason that we have mg cosine of theta is because if we draw a plumb line straight down from M, so straight down, it makes this angle theta with this line that's perpendicular to the surface. I do have in here the proof if you're really curious about the geometry of this, but just for now, take my word for it that it does make this same angle theta, whatever this incline is here, right? So this line that goes straight down towards the center of the Earth, it makes an angle theta with this line that's perpendicular to the surface. So knowing that, we know that opposite that angle, we're going to have, because this vector here is mg, right, going straight down, opposite that side, we're going to have mg sine of theta. Then, of course, on the adjacent side, we're going to have mg cosine of theta, right? And because we have no net vertical movement, you can see once again, we have our acceleration, and it's totally in the horizontal-ish, right? It's moving in this inclined plane. But we can see that this mass isn't bouncing up and down, right? So we, once again, don't have a net acceleration in the vertical. It is strictly in the horizontal, well, the direction that we're going to define as the horizontal, right? Which is this plane here, this x plane that I'm illustrating here. Okay, so if we come over here, essentially all I've done is I've rotated this 30 degrees clockwise just to make it a little bit easier to view the free body diagram. So we just took this, rotated it theta degrees, so we have the normal force, which is equal to a positive mg cosine of theta, then we have negative mg cosine of theta going downwards, right? Then in the direction of motion, in the direction of the acceleration, the force that's driving this motion is mg sine of theta. And then the only force that's opposing it would be friction if we happen to have friction. Not all problems will necessarily have friction. So if we go along and just collect all of our terms and look at things in terms of x and y, then if we sum up our forces in the x direction, we would have mg sine of theta minus the frictional force, right? Because the direction of motion we're going to say is the positive direction. So mg sine of theta minus the frictional force is equal to the total mass of the system times the acceleration of the system. Now the reason I say the acceleration of the system is, remember, this doesn't necessarily just have to be one mass by itself. It can be a system of masses connected to one another by a string or some other means. Okay, and then in the y direction, we have the normal force minus mg cosine of theta, which we established the normal force is just a positive mg cosine of theta, so we can see that both of those forces would cancel out and equal 0, which is exactly what we expect, right? Because our acceleration is only in the horizontal, not in the vertical. Okay? Now let's look at an example where we just don't have friction. So in this one we had Fk. In this one, that's the only thing that's different. Now we don't have a frictional force. So you can see that mg sine of theta is what's driving the system. Now it's being opposed by nothing, right? Nothing is changed in the vertical. So basically, all that would be different here is you would have mg sine of theta is equal to the total mass of the system times the acceleration. And that would be it, because you wouldn't have this term. That's the only thing that's different. And you could probably see here, and we're going to do it on another slide, that these m's would cancel, so you'd just be left with g sine of theta is equal to a, but we'll save that for the next slide. So once again, this is our motion on an incline example where we have no friction. So this is just our picture rotated theta degrees clockwise, just to visualize our free body diagram a little bit more easily. Now, typically when you're asked to solve problems for motion on an incline, you're going to be finding the acceleration, you're going to be finding an experimental gravity value like you're going to do in Lab 9, or you'll be finding what the angle of a slope is for a given acceleration. Okay? So with no friction, this is a pretty simple thing, right? You're pretty much going to have this same equation where you're summing up your forces in the x direction, and it's just mg sine of theta is equal to ma. Your m's cancel, so you have g sine of theta is equal to a. So if you're trying to find your acceleration and you have no friction, that's it. It's just g sine of theta. If you're trying to find an experimental gravity, like you're going to be doing in Lab 9, you're going to have your acceleration divided by sine of theta, right? All you've done here is you've rearranged this equation, so you have g over here, divide both sides by sine of theta, and then you're able to solve for g, right? A over sine of theta. So last but not least, if you're trying to solve for what the angle of your slope is for a given acceleration, you're going to use inverse sine of your acceleration over gravity. The reason for that being, if you look up at this equation here, you can see that sine of theta would be equal to a over g, right? If you divide both sides by g. So we're trying to find the angle, right, which is theta. So we're going to be using our inverse sine. So basically you take your inverse sine of your opposite over your hypotenuse, and that gives you your angle theta. Now, I don't really want to spend too much time on motion on an incline with friction because the pre-lab practice problems are going to be without friction, but I just thought it would be good to introduce it because you probably will see it in your homework problems, and so it's not bad to see it another time. So you can see everything is pretty much the same as it was on the previous slide. You know, the only thing that's different now is that there is friction, right? You can see we have our friction forces back. And I was going to work through one example. So if you're trying to find the acceleration, that's typically the most common thing that you're going to be finding. If you have friction, then when you sum up your forces in the x direction, you're going to have mg sine of theta minus your frictional force is equal to the total mass of your system times your acceleration. So you can see if we write out Fk as mu k times mg cosine of theta, because that's what it would be, right? We know that this is our normal force, mg cosine of theta. Mu k times the normal force is our kinetic frictional force, right? We can see that the masses are going to cancel. So then we would just be left with g sine of theta minus mu k g cosine of theta, and that would be equal to our acceleration. So if you're trying to solve for that on your homework problems, hopefully this is helpful. All right, moving on. So quick little throwback. So why did the dead cat slide off the roof? Well, because it ran out of mu's or mu-s, right? But specifically, because we just, derived these equations, we know that mg sine of theta minus fk is equal to the total mass of the system times the acceleration. So the reason that it slid off the roof is because mg sine of theta was greater than fk. All right, and then last thing before we do some pre-lab practice problems, this is just the geometry proof in case you were curious why these angles would be the same. So feel free to look this over at your leisure, but I'm not going to really spend time on it because that's not really the focus of this video. Okay, so Prelab 9 practice problems. We have 7 of them, and I'm going to get started. All right, so Prelab practice problem number 1. A suitcase of 50 kilograms is pulled with a force of 900 newtons. So you can see I've labeled that our mass is 50 kilograms, and it is being pulled with a force of 900 newtons at an angle of 10 degrees above a horizontal frictionless surface. So this angle here is 10 degrees. This force, as I mentioned already, is 900 newtons. We have no frictional force opposing the motion. And then Prelab practice problem number 1 asks, what is the vertical component of the applied pulling force? So what we're looking for here is, what is Fy pull? Okay, so this goes back to what we did in lab 4, right? Just breaking our vectors down into components. So Fy pull is going to be equal to F pull times sine of theta, or our hypotenuse times sine of theta is equal to our opposite side. Once we plug in our values, we have F pull, which is 900 newtons, times sine of 10 degrees, which is our theta. Fy pull is equal to 156 newtons. Number 2. So same setup, but this time we want to know, what is the horizontal component of the applied force? So Fx pull. So our adjacent side is equal to our hypotenuse times cosine of theta, right? So Fx pull is equal to F pull cosine of theta. We plug in our values. So F pull, 900 newtons, cosine of theta, 10 degrees. So 900 cosine of 10 degrees is 886 newtons. So Fx pull is equal to 886 newtons. And although we're not going to be asked for this, but if we were asked to find what the acceleration of the system was, this right here, Fx pull, that would be the force that's making this system go. So this is what we would be using to calculate the acceleration of the system. All right, number 3. Again, same setup. We still have the suitcase with 50 kilograms pulled at 900 newtons at 10 degrees. But this time we want to know, what is the magnitude of the normal force exerted by the ground? Okay, so just like before, when we were looking at our mass, we're going to look at what's going on with our vertical components of our pulling force, right? So we're going to sum up our forces in the y direction, as we would when we're concerned about normal force. So we have normal forces upward, so that's going to be positive. Fy pull, also upward, so that's going to be positive. Now, because this force is upward, we expect that the surface is not going to be feeling this full weight of mg, right? So when we get our normal force, it shouldn't be quite as big as mg. If it is, we should be concerned. Okay, and then we're going to subtract mg, right, because that is a downward force. So now we've summed up our forces. If we rearrange to solve for normal force, because that's what we're looking for, we get mg minus Fy pull. That's exactly what we'd expect. We expect that our normal force is going to be less than mg. It's going to be less by Fy pull. So mg, 50 kilograms times 9.8 meters per second squared minus Fy pull, which we already calculated, is 156 newtons. So we get that our normal force is equal to 334 newtons. And if you were curious, 50 times 9.8 is 490. So yes, 334 is less than 490. So yes, the surface does feel a force smaller than the weight force. And that's because it's being diminished by Fy pull. All right, so now for number 4, we're going to switch gears a little bit. We're no longer on a horizontal surface. So we have a 3 kilogram box placed on a frictionless slope of 25 degrees. And we want to know, what is the magnitude of the net force exerted on the box? So the net force being what is creating the acceleration, right? What is making this system go? Or in this case, this mass go. So you can see right here, they told us it's 25 degrees, so I've labeled our slope as 25 degrees. This angle also here is 25 degrees, as we've established. The acceleration is in this direction, okay, so it's sliding downhill. We have a normal force, which is equal to mg cosine of theta. That is being opposed equally and oppositely by this downward mg cosine of theta force, which is our adjacent side of this right triangle that we have right here. The opposite side of the right triangle is the force that is making this object move, that is producing this acceleration. So this is the force that we're concerned about. So mg sine of theta. Okay, now if we rotate it theta degrees clockwise, just so that it's a little bit more easy to visualize, right? As I mentioned, the net force that we're concerned about is mg sine of theta. Well, mg sine of theta is just 3 kilograms, right? M times g, 9.8 meters per second squared, times sine of theta, which is 25 degrees, and we get that this is equal to 12.4 newtons. All right, number 5. As the box slides down the slope, what is the acceleration of the box? So as we talked about, mg sine of theta is what is producing this acceleration A, right? So when we sum up our forces in the x direction, it should come as no surprise that because it's a frictionless surface, all we have is mg sine of theta is equal to the total mass of the system times the acceleration. Now these masses are the same, so they cancel with one another. So as we talked about in the other slide, we're just left with g sine of theta is equal to A. So we plug in our values. G is 9.8 meters per second squared times sine of theta is 25 degrees. And we end up getting that our acceleration is equal to 4.15 meters per second squared. All right, pre-lab practice problem number 6. How must the angle of the slope be adjusted to reduce the acceleration of the box to 1 meter per second squared? So we know initially when they gave us the information that we had a slope of 25 degrees, and this slope of 25 degrees produced an acceleration of 4.15 meters per second squared. Now what they're telling us is that the acceleration needs to be 1 meter per second squared. So we expect both the angle and the acceleration to decrease, right? Because they told us the acceleration will now be 1 instead of 4.15, and before it was 25, and we expect that it's going to be smaller than 25, right? This makes logical sense. So we set up our forces in the x direction. Once again, it's still a frictionless slope, so we have mg sine of theta is equal to ma. The m's cancel, so we're left with g sine of theta is equal to a. Now we know that sine of theta would be equal to a over g, right? And we know both of these values, a and g. They told us a is 1, and we know that g is 9.8 meters per second squared. Now we're looking for theta, so we're going to use inverse sine. So sine to the minus 1 of a over g. We plug in those values, right? So we have a is 1 meter per second squared divided by g, which is 9.8 meters per second squared. And we get that the new angle, in order for this acceleration to be exactly 1 meter per second squared, the new angle would be 5.9 degrees. And this, of course, makes logical sense with what we were expecting. We expected the slope of the angle to be less than 25. This certainly is less than 25. So that all checks out. All right, last but not least, pre-lab practice problem number 7. We have a slope that is 0.64 meters long, and it was adjusted such that one end is 2 centimeters above the other, as shown in figure 4. This should probably sound pretty familiar if you've already watched the video on Lab 9. This is almost exactly what the setup looks like. So what we want to do is we want to calculate what is the angle of the slope, unlike Lab 9, because you won't be calculating the angle of the slope. You'll just be finding sine of theta, not theta itself. But if we wanted to do that, so this is the graphic that they give you in the pre-lab. Okay, now I think it's a lot easier if we view it as a right triangle, so basically just cut this whole trapezoid part off and look at it as a right triangle. So here we have that right triangle. Okay, so the hypotenuse, as they mentioned, is 0.64 meters, but they said one side is 2 centimeters above the other, so you can see this opposite side here is 0.02 meters or 2 centimeters above the other side. Okay, so we're trying to find the angle theta. So we're going to use inverse sine of our opposite side over our hypotenuse, both of which were given. So this is a really straightforward plug and chug problem. So 0.02 meters divided by 0.64 meters, and we get that our angle is 1.8 degrees. So this angle theta here is 1.8 degrees. So that's it for the pre-lab practice problems for Lab 9, but as you know, the quiz is going to have 5 questions from last week, which was buoyancy, and 5 questions from this week, which is incline motion. So if you want to stay tuned, I am going to go through a few buoyancy review questions just to make sure that's all fresh in your mind before you take the quiz. All right. So last week we talked about this concept of specific gravity, and basically what specific gravity is how much of an object is submerged, okay? And the way that you calculate specific gravity is you just take the density of your object, divide it by the density of your fluid, and whatever fraction you get at the end, that tells you what amount of the object is submerged. So I think the best way to review this is just to go through an example. So let's say we have a 30 centimeter wooden block with a density of 650 kilograms per meters cubed, and it's floating in water, okay? And the density of water is 1,000 kilograms per meters cubed. What length of the block is submerged, okay? I've only given you one dimension, so 30 centimeters is what we're working with. Okay, so to find the specific gravity, we're going to divide the density of our object by the density of our fluid, so 650 by 1,000, so we get 0.65. Now, in order to figure out how much of it is submerged, we're going to turn around and take that fraction that's submerged, and we're going to multiply it by our given length, right, which was 30 centimeters. So 0.65 times 30 centimeters, that gives us 19.5 centimeters are submerged in the water. Which would, of course, mean that 10.5 are outside of the water or not submerged. All right, so more buoyancy review. So we established in the lab that buoyancy force, it can be calculated a few different ways. One of those ways is we can subtract our weight in air, as you did with the hanging metal ball. We had the weight of it in air, and then we submerged it in water, and then we got the weight again. The difference between those two forces is the buoyancy force, right? Then we also talked about, and this was the first thing that we discussed in the pre-lab last week, that buoyancy force is equal to the mass of a fluid that's been displaced times gravity. So essentially what buoyancy force is it's the mass of the fluid that's been displaced times gravity. It's the weight of that water that's been displaced or the weight of that fluid that's been displaced. And then another thing that we talked about in the pre-lab last week was that the weight of an object in air is of course equal to the mass of the object times gravity, right? This is just the definition of what weight is. It's mass times gravity. So now I have a question to kind of put a bunch of concepts together from last week. So we're going to calculate the density of that metal ball from last week, given just the weight in air and the weight in water. So the weight in air that we're given is 2.39 newtons, and the weight in water that we're given is 2.12 newtons. Now recall, of course, that buoyancy force is equal to the weight in air minus the weight in water. And also buoyancy force is equal to the mass of your fluid that's been displaced by an object times gravity. And weight in air is equal to the mass of an object times gravity, right? The definition of weight. And then we know that the density of water, it's being given here in case you forgot, but it's 1,000 kilograms per meters cubed. So now we're going to take all of this information that we know, and we're going to solve for what the density of the ball is, okay? So if we're trying to find the density of the ball, it stands to reason, of course, that we want to find the mass of the ball, and we want to find the volume of the ball, right? Because the mass of the ball divided by the volume of the ball will give us the density of the ball, which is what we're looking for, okay? So things that we know about the mass of the ball. Well, we know, first of all, that the weight of any object is equal to the mass of that object times gravity, right? So that means that if we rearrange this equation, we know that the mass of the ball is equal to our weight in air divided by gravity, right? And we were given the weight in air, and we know what gravity is, so we can easily calculate the mass of the ball, right? So we know the weight in air was 2.39 newtons. We know gravity is 9.8 meters per second squared, so that means that the mass of the ball is 0.243 kilograms. Number 2, we're going to find the volume of the ball. Okay, so this one's a little bit more complicated. It just takes a little bit more thinking. So we know that the volume of the ball is equal to the volume of water displaced by the ball, right? We know the volume of water displaced by the ball is equal to the mass of the water displaced by the ball divided by the density of the water, right? We've just taken the density equation, mass over volume, and we've rearranged it to solve for volume, right? Which is mass over density. We also know that the buoyancy force is equal to our weight in air minus our weight in water, okay? So if we calculate our buoyancy force, that would be 2.39 newtons minus 2.12 newtons, and this is equal to 0.27 newtons. Okay? Now, the definition of buoyancy force, as we talked about, is the mass of the fluid, or the water in this case, the mass of the water displaced by the ball times gravity. It is the weight of that water that's been displaced, right? So, if we rearrange, we can solve for what the mass of that water that's been displaced is, right? So we're just going to divide both sides by gravity. Buoyancy force divided by gravity is equal to the mass of water that's been displaced, right? So buoyancy force, 0.27 newtons, gravity, 9.8 meters per second squared. So the mass of water that was displaced by that ball is 0.02755 kilograms, okay? Now, we know what the density is, right? We know it's 1,000 kilograms per meters cubed. So we now have the volume of the ball because it's the same as the volume of water that was displaced by the ball, right? That's exactly what Archimedes' principle says. So mass of the water, which we just calculated, is 0.02755 kilograms divided by the density of the water, which we know is 1,000 kilograms per meters cubed. And now we have the volume of the ball, right? So that's 0.0002755 meters cubed. Now the last step, very simple, right? Just mass divided by volume to get density. Okay, so the mass of the ball, we calculate that up here, 0.243 kilograms. The volume of the ball, 0.0002755 meters cubed. And we get that the density of the ball is 8,820 kilograms per meters cubed. And that's all she wrote. So hopefully you found these pre-lab practice problems helpful, and best of luck on quiz 9.